All right, so I think we've kind of stabilized here on people joining. So I think without further ado, we'll go ahead and kick things off this morning. So welcome to the Calcium Products 2025 September webinar. So this will be for our first session. Both sessions today and tomorrow, Wednesday, will be at the same time, 10 o'clock to 11 o'clock, and they will be the same presentation. So if you are on today and we're planning on being tomorrow, we'll just be going over the same material tomorrow as what we will today. Want to welcome you and thank you for your time. First off, my name is Josh Enderson. I'm a technical sales agronomist with Calcium Products, been with the company a little over a year now. I am joined by my colleagues, Glenn Howell and Andrew Hoiberg. They will be assisting in the presentation today. Guys, if you want to take a few seconds, go ahead and jump on, introduce yourself, and say hi to the group.
Yep. Hey, morning. My name is Andrew Hoiberg. I'm in charge of the research and development and agronomy arms here at the Calcium Products. Appreciate everybody's time here this morning. And, I would just offer that we've got a chat window. So if anyone has any questions or comments throughout the presentation, please feel free to put your questions and comments into that chat window, and I'll feed those over to Josh as anything gets put in there. And I appreciate everyone joining today. Thanks.
Hey, good morning, everyone. Glenn Howell here, living in Nebraska, and appreciate everybody joining us this morning. Look forward to some great content and interaction. As Andrew mentioned, please join us with a chat or question on those things, and we'll make sure we get those addressed during our time today.
All right, thanks, guys. One thing before we get started, we have requested CEU credits for this webinar. We haven't really gotten confirmation back yet. I'm assuming we will shortly. So we don't have a QR code right now, but if you are on the webinar and would like to get those CCA credits, there'll be some instructions later on. Just drop us an email at agronomy@calciumproducts.com. Let's go ahead and get things kicked off. All right, so first of all, the title of this webinar is going to be Soil pH, Liming Materials, and the Cost of Your Growers' Low pH in Their Soils. So we kind of have this broken down into 4 quadrants. What is soil pH? Why is it important? What are some things that we're doing from a soil fertility standpoint that can affect soil pH? And what are some materials that we can use to correct those low pH situations that we might have out in those fields? Thirdly, we'll dive into our own product, 98G pelletized limestone, and talk about some strategies that we can use with that, specifically our maintenance strategy and the benefits that are wrapped up in utilizing that strategy for your growers. And then finally, if those of you pay attention to your emails from Calcium Products, we launched a really nice tool, kind of a calculator that we'll go through. Glenn will actually go through in more detail towards the end of the presentation that can actually quantify monetarily the costs of some of those low pH situations that we have in the soil, and from a fertilizer efficiency and lost fertilizer investment dollars due to low pH. And we'll cover that at the end of the presentation. All right, so a little bit about soil pH. First, just kind of the basics. Obviously, soil pH or also known as water pH is often referred to that active acidity that's in that soil solution. From a very basic terms, pH is simply the logarithmic scale of the concentration of the hydrogen ions in the soil. So if you think about that, because it's measured on a logarithmic scale, we all know that it's not necessarily moving from a pH of 7 to a pH of 6 isn't just one increment. That pH of 6 is actually 10 times more acidic than a pH of 7, and then so on and so forth as you move down that scale, because it is a logarithmic scale. Very simply, when you send soil samples to a soil testing lab, they're going to take those field-dried soil samples, a very small increment of that overall composite sample. They're going to add water. It's usually a 1-to-1 ratio. They're going to let it sit blend and let it sit for a little bit, and then they'll just measure it with a pH probe. So very simple process from a soil testing standpoint. Switching gears to soil buffer pH, this is often referred to as reserve acidity. And so we like to, at Calcium Products, we like to use kind of the metaphor of the bicycle and the tractor tire there you see on the left. And what buffer pH is really going to do, it's going to measure that soil's ability to resist changes in pH. This measurement is very, very key in determining lime amendment requirements, even as so on as soil fertility applications as well. It's measured by taking that same solution that we worked with the or the same soil sample, adding in a buffering solutions. Typically that buffering solution is going to be about a pH of 7.5. So we're adding in a higher pH solution, and we're going to record how that soil sample changes in pH. If there's a big change, then we know it's probably not going to take quite as much lime to bring that soil pH to where it needs to be. If it doesn't move a whole lot, then it's probably going to take a little bit more lime because that soil has a high buffering capacity. The soil buffer pH can very easily be influenced by soil structure and soil texture characteristics, specifically clay and organic matter content, and as well as cation exchange capacity. So the higher any of those three characteristics are, generally speaking, the higher buffering capacity your soil is going to have, and the more liming material it's going to take to actually change that soil's pH. But getting back to the diagram we have here on the left-hand side to put soil buffer pH into a nice understandable way here, if we think about adding air to a bicycle tire versus adding air to a tractor tire. So if we want to take, for instance, this bicycle tire and change it from 40 psi up to 50 psi, it's probably not going to take as much air volumetrically to change that pressure in the bicycle tire as it would if you were inflating, say, a rear tractor tire. So that's, if you can think about it that way from a buffering capacity standpoint, those higher buffering capacity soils, high organic matter, high CEC soils are going to act more like the tractor tire when we're trying to adjust soil pH. So a little bit about soil pH and what things in the soil and activity in the soil is driven by soil pH. So obviously everybody on the call, I would hope, has seen the diagram on the left. So number one, it's going to be tied to the availability of most essential and non-essential nutrients, all the way from nitrogen down to all your micronutrients that we're using in trace amounts for that growing crop. Secondly, it's going to be a driver of microorganisms and fauna in the soil. So a lot of biology, bacteria, fungi, diseases, things like that. It's also going to be tied to your abilities of the soil to hold cations. Me being a former seed guy or former Corteva employee, we talked about herbicide performance and expression of genetic potential a lot of times in front of groups, and soil pH can be a good indicator of the ability of those residual products to perform and resist breakdown in the soil. So from a residual herbicide standpoint, pH can be important, and also the expression of that corn hybrid or that soybean variety or wheat variety or alfalfa variety to express the full potential of those genetics is going to also be connected to soil pH. So kind of on this next slide, we know soil pH is important, and really to break it down into three key aspects here, we know it can be important from a yield potential standpoint. So over on the left-hand side here, you see a diagram. This was created by Smith and Doran back in 96, and really a lot of people agree with this sort of research, and different crops behave differently based on their soil pH level. Some are not as responsive to soil pH, as you can see on the chart there, and then others are very responsive. If you look at alfalfa in particular, alfalfa, we know that requires a much higher pH in order to get optimum yield potential out of that growing crop. In the middle here, you see nutrient availability, as we kind of hit on that on the last slide as well. And this is really what that calculator that we're going to talk about at the end is built around. So you can see how the availability of macro and micronutrients and even some nutrients that we don't necessarily want or need, aluminum in particular, can be tied to soil pH. So in the case of aluminum here, you can see it's kind of that ladle-shaped curve towards the bottom here. At our typical soil pHs, aluminum is not very available, and that's good for our growing crops, so you don't see things like aluminum toxicity or clubbing roots, specifically in corn, with that aluminum toxicity. But if you get pH outside of your optimum range of below 5.5, that aluminum becomes hyper available in that soil solution, and then we can see issues like aluminum toxicity from a crop standpoint. Finally, here on the right-hand side, you have biological activity. So you can see how different bacteria and fungi favor or are optimized at certain pH ranges. And so that's obviously can be for good or for bad bacteria and fungi. So fungi that can cause disease, fungi that can be symbiotic in the root zone with our growing crops as well. So what are some actions that our growers or we ourselves are doing that can affect our soil's pH, and how does that kind of cycle? So number one, first and foremost, probably the most acidifying factor of our soil's pH is going to be that first bullet point there, the conversion of ammonium to nitrate, leaving free hydrogen. So as we talked about in one of those first slides, soil pH is literally the concentration of hydrogen ions in that soil and on the CEC. So anytime we're converting ammonium to nitrate or even denitrifying in some of our waterlogged soils, lack of oxygen, we're releasing hydrogen ions to then adhere to that soil's colloid, become part of the CEC, and in fact acidify the soil solution. Secondly, we have the oxidation of elemental sulfur. So anytime your growers are applying elemental sulfur, maybe it's going to be coming up this fall, we're applying straight S as a singular element to the soil solution. For that to become plain available, it has to convert to sulfate, and to do that, it will release hydrogen ions from water molecules as it tries to pick up more oxygen molecules to become sulfate or SO4 and be able to be uptaken by the plant. So we know that takes biological activity, takes moisture, takes heat, takes time, but that is a very, very high level of acidification when you're using elemental sulfur as your sulfur source. The next two here are going to be a little bit more minor in current day and age. So we have number one being rainfall, leaching of basic cations that can buffer that pH change. So things like even sodium, potassium, some of those basic cations that we need in there can be leached and then causing more acidic situation in that soil solution. And then before the Clean Air Act was inducted decades ago, we had issues with acid rain, so acidic rainfall from atmospheric CO2 coming down and really acidifying that soil, that topsoil, as it was happening. That's not such of an issue today as it was decades ago. But again, it's another action that can affect our soil's pH. And then finally, the plants or the growing crops uptake of those basic cations that we talked about with the first couple points here. So anytime your plant's taking up those basic cations, it leaves room on your soil colloids for hydrogen to take its place, whether it's a potassium or magnesium or things like that. It will leave place for hydrogen to come in and contribute to acidity. So switching gears here, going back to that first bullet point that we had, anytime we're applying ammoniated nitrogen source, we are contributing to soil acidification. So on the left-hand side there, you see a lot of different nitrogen sources, whether it be anhydrous, AMS, MAP, or DAP. And you see those nitrification reactions and how they take place in order to release the nutrients that the crop can then take up. And if you look at every single one of them, right after the arrow there, you see a H+. You see a 1H plus or 2, 3, 4H plus. So that reaction is in fact releasing hydrogen ions into the soil solution, which are then in case going to acidify our soil. So from a volume standpoint, here in the central corn belt, we use a lot of anhydrous ammonia. So that's probably going to be our biggest source of soil acidity from a nitrogen standpoint. But know that even when you're applying MAP or DAP or your phosphorus applications this fall as well, those products do also contribute to acidity in your soil solution. So to kind of put that into picture format here, we went ahead and we have a calculator where we can take these ammoniated nitrogen products and calculate just exactly how much calcium carbonate is going to be needed to neutralize all the acidity that application is putting into our soil. So this is going to assume that we're applying 100 pounds of each one of these products on the left-hand side. So you got some of your phosphorus sources. At the very top, you have our very own SO4 pelletized gypsum. That's going to be a pH neutral sulfur source. So if you're looking for a sulfur source that's not going to change pH, that's going to be your primary option. And then we're gonna see like some of these phosphorus applications. If we're applying 100 pounds of MAP or DAP, you're going to need between 60 to 65 pounds of pure calcium carbonate to neutralize that application. As we go down here, you see elemental sulfur, you see some urea and AMS, and then at the bottom here, anhydrous. So we're taking some assumptions into consideration with this calculator. We're going to assume that all ammonium over here, this right bullet point, converts to nitrate. Now we understand that's not going to happen in all cases. You're going to have that plant uptake some of that ammonium before it gets the chance to convert to nitrate. So consider the numbers that you see here to be kind of that quote unquote worst case scenario. We also are going to consider that when we're applying that elemental sulfur, all of that's going to contribute to and be turned into SO4 and be plant available. The asterisk here, you see, obviously we know not many farmers are going to want to apply 100 pounds to the acre of elemental sulfur. So this number is representing a 25 unit sulfur application using 90% sulfur product. So we're actually applying just short of 28 pounds and needing about 80 pounds of pure calcium carbonate to neutralize that single application with elemental sulfur. Switching gears to some liquid products to just see, okay, our dry products aren't the only products that are going to contribute to soil acidity. The liquid ones do as well. So the top three there, you have some very commonly used starter fertilizers. So this is going to be pounds of calcium carbonate needed to neutralize each gallon of application. So some of these starter products typically 4 or 5 gallon rate. So you can multiply that number by 4 or 5 or however many gallons per acre your grower is using. Same thing with 28%, 32%, and then ammonium thiosulfate as well. So you can see some of those as that nitrogen concentration increases, so does the amount of calcium carbonate needed to neutralize the acidity that you're contributing with those applications. So to talk a little bit about some liming materials and maybe a little bit about how they compare and stack up against each other, I'm going to kick it over to Glenn to cover this section.
Thanks, Josh. So there are a variety of liming materials available today. Some pictured here are some common ones that you may encounter. So 98G pelletized limestone on the upper left, a sugar beet or waste product limestone, maybe it's water treatment lime in the upper right, as well as in the bottom right. And then on the bottom left, obviously, as we apply different materials, they have different characteristics as far as how they apply or how well they can be done. So as we dig into how lime material works overall, in essence, what we're taking is a calcium carbonate or magnesium carbonate, which is a dolomitic type of material. In either case, we're taking both of those materials, combining it with the hydrogen in the soil represented by the low pH. And our end products are water, carbon dioxide, and what was hooked up to or attached to the carbonate molecule of the liming material. So All liming materials are rated based on their pure calcium carbonate equivalent. So that refers to as the material as it is mined or as it is initially produced. What is the quality of it? What's the purity of it? And how does that compare against the standard? The second part of the liming score is based upon particle size. So limestone is a very insoluble type of material. So smaller particle sizes improve the solubility or maximize the solubility available from a given material. In most cases, lime scores are based on like a 30 mesh and a 60 mesh. So a mesh representing a 1 inch by 1 inch square, more wires or more mesh size, or a larger score represents a smaller opening between each wire. And so that improves the solubility of that material compared to a coarser, less fine ground material. So each state basically has kind of their own nomenclature based on how their particular legality standpoints are put together. But in most cases, it's just a way to compare different sources of liming material across a landscape, so you can compare apples with apples based on your particular conditions and locality to compare one liming source versus another. One of the considerations for particularly water treatment and sugar beet limestone, and for those who are unavailable, beet lime would be from a sugar beet processing facility where they're taking and reacting the ground up beets with a reagent to extract the sugar out of those and end up with a waste product or extra product left over, termed beet lime or sugar lime. And they're both water and beet lime have a very wide range of characteristics. Typically, they're not a very uniform material, both in terms of their purity or in terms of their dry matter. So they have a lot of water. They make it very difficult to spread effectively. In addition to their varying qualities, make a difference on how effective they can be. And in general, a lot of times they also have leftovers. So whether it's from a water treatment facility or from a byproduct type of limestone, things like heavy metals often are something that are present and definitely are something that should be monitored or at least tested for if that's a material that's being considered for use. So here we call what we describe as called an aglime stack. So this is the whole sample, top to bottom, represents a single sample sieved into different particle sizes. So at the top there we have a very coarse type of material, so like a 4 or 8 mesh. At the bottom we have a very finely ground material. Put a red, green, and yellow analogies to those based on our feelings on how effective those can be. So at the top we have a 4, 8, and a 30 mesh. Those are materials that are going to be somewhat effective, but not very effective quickly, and certainly not really effective compared to some of the other materials at the bottom. So very coarse materials at the top, very finely ground materials at the bottom of the stack. The challenge with the very finely ground materials are that's the absolutely the best material for effective liming results. So a change in the pH, we want something that's ground very fine. A challenge with the finely ground materials are they also have a tendency to move with very little air movement. So a 5-mile or even a 15-mile-an-hour breeze during time of application, materials are usually pretty dry. So these materials will float across a landscape very effectively, which is great if you're downwind of somebody spreading ag lime. But if you're the one paying for that cost, really there's some concerns about, what am I getting and how much am I paying for that? And then the green there's kind of the sweet spot. So in an ag lime type of material, a 60 mesh is probably the right spot to have a particle size being a combination of fine enough to work and coarse enough that it's still going to land where you want it to. One of the concerns, again, overall, is just looking at that same stack is how much of it is really too big to be effective, how much of it is really fine and will be effective, but tends to move somewhere else, and how does that look like over a period of time? So based on some studies that were done and repeated over a bunch of years, many decades ago, really, the coarse materials are going to have some effectiveness in the next 12 months and a little bit more over a 4-year time frame. So like a 30 mesh material, 3-4 years down the road, we're talking about half of that material is going to be effective based on its particle size. Again, that really fine material is going to be very effective initially and also has a longer lasting effect. So it's not really a trading off one for another for a fine particle size limestone. It's just a case of how am I going to get it onto the ground effectively. So looking at today's environment, we use a lot of large equipment. I've noted before that a lot of the things that we do in agriculture, specifically agronomy today, our parents, our grandparents would recognize in some way. We don't plant with a two-row planter, we don't plant with a horse material, but we do plant corn, and the material looks, the equipment looks somewhat the same. They would kind of figure that out. Aglime probably is a single material that they would easily recognize because, again, we're not doing it with horse and buggy, but we're still using the same type of material to do a very crude, effective way, but changing pH in today's environment. And as I mentioned before, again, it takes a very little wind speed to really have a big effect on drift loss from an aglime application. In other words, 15% of a 10-mile-an-hour wind is going to drift off target based upon those type of characteristics. Certainly, you're going to have a case of where you're going to have a little bit more, a little bit less, but in general, there's a larger percentage of aglime that tends to drift off target as particle sizes decreases, which again is the most effective materials we want to use. So it's kind of a compromise for sure, and it's just a matter of does this really fit in today's environment with economic, agronomic considerations that we have. On our website, calciumproducts.com, we have an aglime map. So this represents varying samples collected across the Midwest, characterized on their different types. So we've got circles for aglime, sugar beet limestone, as well as byproduct type of materials. If you bring this map up and hover over any one of those samples, you'll get a screenshot like you'll see there on the right. It's going to show you where it was collected, chemical characteristics of it for both calcium and magnesium, and overall limestone purity, as well as an effective calcium carbonate, which is going to again take into account purity plus particle size. Any things for considerations for contaminants such as aluminum, which in this case was not present, but often can be in byproduct limes. And then a comparison of how much of 98G compared to this material. So in this example, it would take 9 pounds of that material, aglime, to compare to 1 pound of 98G on a effective liming consideration. So those are some things we just talked a little bit about. Josh is going to go back and dig into things a little bit more specifically at this time.
Yeah, thanks, Glenn. I think one thing I'll mention before we go ahead and leave this slide here was if any of you on the call see a dot of your local quarry that's maybe, or you know of a local quarry that's maybe not on there, go ahead and reach out to your local calcium products sales manager, and we can go ahead and grab a sample from that, or if you could grab a sample and send it in, we could get it analyzed and get it updated on this map. And also what we do, we can also provide the aglime stacks like Glenn was talking about a couple slides ago. Those can be a really great talking point for grower customers when having that aglime discussion. So if you have any interest in doing that, go ahead and reach out to your local sales manager. So switching gears here, we talked about some alternative liming sources, but now we want to spend a little time talking about our very own 98G pelletized limestone. So our liming source with calcium products. So its namesake really is going back to the fact that it's made from 98% pure calcitic limestone. So it's a very pure, very pure portion of limestone or vein of limestone. Located in north central northwest Iowa. It's actually going to be a 36% calcium and under 1%, under a 0.5% magnesium. So it's a very high quality calcium carbonate source. We take that limestone and we grind it very finely into about where 90% of it's going to pass a 100 mesh sieve. So if you think back to that lime stack that Glenn showed you and talked about, a huge portion of that overall conglomerate of the ground product is going to be on the lower end of those aglime stacks. So we maximize surface area, maximize our reactivity availability with the fine mesh that we grind this product to. It's so fine that in our newest plant we actually move it with air, if you think about that. We then take it, we mix it with water and some binder and pelletize it through a process we call pan agglomeration. It's kind of a very scientific process and can be altered by different environmental factors in the plant as well. So we're always trying to get to the point where we can achieve that ideal reactivity. So it's going to break down and neutralize pH like we say it can and will when it gets applied to your growers' fields. But also we want to maintain pellet strength and make sure that we're delivering strong pellets that are going to withstand the rigors of handling multiple times in your guys' facilities before they're spread. We feel like we're kind of walking that razor's edge between those two, but again, know that we're always looking for improvements there, whether it be dust or pellet strength. And I think we've gotten a really good balance there in reactivity and durability of our product. And with this product, you can very efficiently and effectively correct or maintain your grower's soil pH. So how does 98G stack up to some other pell-limes or some other competitive products we have out there in the marketplace today? So you can see the table on the left there. You can see from the get-go, 98G, we're starting with a much higher quality limestone product, higher CCE, and especially after we do our proprietary grinding, a much higher ECCE, or effective calcium carbonate equivalent. And so really that gets us a kind of a head start right out of the gate before we even start that pelletizing process. And so again, how do we stack up? Again, we're going to be made from, we're going to start with higher quality limestone product. We're going to grind it more finely. I think we pride ourselves on how rigorously we test those products in our plants, both for pellet strength and for solubility. We're going to be one of the few pell-limes that are actually OMRI certified. So for the organic grower out there, and really we believe that when it comes to pell-limes, it's really 98G, and then there's everyone else because our product, like I covered in those bullet points, we start with a more high quality product. We do a little bit more. We go that extra step in the process to make sure that you're getting the best possible product from the raw materials that we start with. Next here, we have a little bit of a solubility video to show how solubility differences can affect your ability to neutralize acidity in the soil. So we have 3 different liming sources here. In the very middle, we have our own 98G. On the right-hand side, we have a Western Iowa pelletized lime. And on the left-hand side, we have a pretty, generally speaking, high-quality aglime. So what you're going to see here as I start this video is going to be, we're adding each one of these lime sources into vinegar, so a slight acid that's filled up to that red line, and you're going to see that effervescence. So that's going to be that pH being neutralized, the lime going to work. And as you can see with the aglime, we solubilize those small particles rather quickly, but then that effervescence dies down rather quickly because all that's left are those coarse particles. Similar with the Western Iowa pell-lime, as those pellets kind of break down, you get some pretty good effervescence, but then eventually it plateaus and dies out. Lastly, here with the 98G, you can see as those pellets start to break down, you get very rapid reaction right out of the gate, and that reaction continues to sustain as we get to the end of the video here. You can see it still working as those pellets are continuing to break down and release that ultra fine, highly effective particle size within that vinegar solution that we have there, just showing how quickly and how effectively 98G can neutralize pH compared to some of our competition. Kind of building off of what you saw on the last little video there, Iowa State did a study back in 2018. Back in 2018, we did some research where we took 3 different liming materials, one of them being our own 98G. We also used a calcitic and a dolomitic aglime, and they applied the same volume of ECCE, so same number of pounds of ECCE to a soil whose pH was 5.5. So they compared these 3 lime sources and wanted to see how they compared to what the industry considers the benchmark, which would be 100% calcium carbonate equivalent. And so you can see the graph on the right, they map that pH change through incubation across a period of time. So as you see there, they started with a pH of 5.5. They applied the same number of pounds of ECCE to each one of those soil samples, monitored the pH. So if our state liming recommendations and lime rating system is working how it should be, each one of those lines should mimic the calcium carbonate equivalent line. So they should all be right on top of each other up by that green line. The unfortunate thing is the only one that came remotely close was our own 98G. So that calls into question, maybe we've been vastly under applying aglime for the better part of several decades, as you can see with this research here, by maybe overestimating the availability and the solubility of some of those coarser particles, especially when we're thinking about that calcitic or that dolomitic aglime. And so what you can see the research found here, 98G raised the soil pH 0.7 and then a full unit higher than the calcitic and the dolomitic aglimes respectively. So if you think about that, comparing apples to apples, the dolomitic aglime versus 98G, is that soil is going to be 10 times more acidic than the one that was treated with 98G. The other thing I want to call to your attention was you can see there is still slope to this line of the 98G line as you get further out in that incubation time. So a lot of people think of pelletized limestone sources just being a quick fix, a band-aid for 1 year, and then you get quick reactivity to bring that soil pH, but then it doesn't stay there. And this research actually shows the exact opposite of that, where that reaction does have some staying power, and we're continuing to get more and more neutralization as we go further on in time with this incubation study. Switching gears here, a little bit of what we've been promoting at Calcium Products for the better part of the last 7 or 8 years has been our maintenance program. So what is that, and what are some benefits that your growers can expect if they're practicing this maintenance program approach? So we found through some of our research trials that to neutralize some of that active acidification, whether it be a nitrogen application, an elemental sulfur application, or a starter application, you can actively neutralize that acidification by, generally speaking, using a 1 pound of 98G per 1 unit of N applied. What we found is that's going to allow your growers to proactively, not reactively, manage their pH. So we're not riding that roller coaster of pH like they could with the typical aglime strategy. These applications are going to be more frequent and at lower rates than what you would expect with an aglime strategy, usually in that 200 to 250 pounds per acre of 98G. And what we really want them to do is we want these applications to look and feel like a dry fertilizer application, because our product can be blended with any of your other dry fertilizer products that you're going to go out this fall or maybe next spring and apply to your growers' fields. And so really that calls into point the application flexibility and the flexibility when blending with 98G. There are some trade-offs between full neutralization versus maximum economic returns. Our trials have shown that over the years. For full neutralization, you're probably looking at closer to a 1.5 to 2 units of 98G per 1 unit of nitrogen. But when you get to that ratio, the economics just aren't always there, where our maximum economic return has fallen over the years and in our past research trials to be right at that 1-to-1 ratio, where guys are getting a nice yield bump and they're really helping that soil pH stay optimized for the following growing crop. So why are we promoting a maintenance rate? Well, it's really depicted well in this image that you see on the screen here. So comparing the 98G maintenance strategy, the orange line here, versus the gray line, which is going to be our aglime strategy, quote unquote. So you saw with that reactivity assessment where 98G is going to do a better job correcting early on and sustaining that reaction, which allows us to have a lower target, to benefit from having a lower target pH to really optimize and maximize that corrective effect. So you can see here with the quickness of correction, we're gonna take a nice yield benefit in that first year after application. You fast forward another year, we're going to apply a maintenance rate. So that 200 to 250 pound application with 98G, we're going to stabilize our soil's pH for the crops in between. And then this image here specifically is dealing with corn. But you can expect your soybean crop in there as well to have a nice yield benefit as well, especially with soybeans being a more pH dependent crop. But again, with that maintenance strategy, we're going to have a nice benefit at the end of it as well when that aglime is exhausted, and then you start seeing more acidification take into place as we tail off with that aglime strategy. And like I said earlier, kind of ride that roller coaster, that 4 or 5 year strategy with aglime versus 98G, maintaining that soil's pH, keeping that pH where we can maximize nutrient availability and optimize our yield potential. So what's some data that we've seen with our trials over the years with this 98G maintenance rate? So we've done a lot of trials throughout the Corn Belt, both with third parties and in grower fields. So you can see here we're averaging about an 8 bushel advantage in corn when we're applying about a 250 pound application of 98G. A lot of these trials were applied in the spring, not all of them. So that just calls into a point that the reactivity and the speed of reaction, and that even if you're applying liming 98G pelletized limestone in the spring, you can expect to get that pH optimized rather quickly with the speed and effectiveness at which that Iowa State trial showcased a few slides back. Looking at soybeans from a relative yield standpoint, we're seeing about the same percentage relative yield uptick with these maintenance trials. The only difference is with soybeans, we're applying a little bit lower rate. So you can see the average application rate is right at about 50 pounds per acre less in soybeans that are garnering us about a 2.5 bushel increase in soybeans by optimizing that pH. And increasing our specifically phosphorus availability and getting more nutrients into the plant because the availability is just in a better situation with these maintenance rate trials. So what are some soil health benefits that your growers can expect by taking part in some of these maintenance rate trials? So as Glenn mentioned here, it's actually the carbonate, not necessarily the calcium, that's going to be responsible for neutralizing that soil's acidity. So when that carbonate reacts and neutralizes the hydrogen in the soil solution, you're going to be left with water, carbon dioxide, and that nutrient. So in 98G's case is going to be calcium. So you're going to add calcium to the soil, which can then affect your soil's base saturation, building calcium, and then it's going to get rid of some of that hydrogen that's going to be located on your CEC, which then can also lower the base saturation percentage of hydrogen, which is one things a lot of growers want to do. And at the same time, you're going to build calcium, which I think I've never met a grower that doesn't want to lower hydrogen and build calcium in their soil test values from a base saturation percentage. And really, those higher calcium levels are going to help build and improve soil structure. So we know calcium is a flocculating cation in the soil. So what that means is it wants to bring other soil particles together. So what happens when you're flocculating soil particles in your soil structure? That's going to open up pore space for things like water and air to move into that pore space. It's going to increase water infiltration, and it's going to build just overall soil health. It can help with compacted areas. Help with areas that we have high sodium from manure applications or irrigation water issues. It's just going to open that soil up and become a more healthy environment, not only for roots, but also for some of those beneficial microbes as well. We've also got some really nice economic value by using the 98G maintenance strategy here. So you can see we're comparing our very own 98G versus what we would consider a very high quality aglime. So you see what I have circled there, ECCE of 73. If you look at that liming materials map on our website, you're going to be hard pressed to find a lot of aglimes that have a higher ECCE value than that. But you can see even against a very high quality aglime and soil pH conditions, you can see here we're starting at a 5.7 and wanting to bump that up. So we're getting a corrective application in early and a maintenance application in year 3. You can see here this was what I would consider almost worst case scenario. You're going to return some profit per acre to that grower by utilizing 98G to get that reaction taking place quickly and effectively, get that pH where it needs to be, and then in year 3 apply that maintenance strategy to keep that pH at the optimum level where you can then maximize your nutrient availability and optimize your yield potential. We've got some calculators like this if you want to kind of get some comparative things going versus your own local aglime. Go ahead and reach out to your local calcium products rep, or go ahead and drop us an email at agronomy@calciumproducts.com if you really want to get more into the weeds on the economic side of 98G and this maintenance strategy. But we're very confident in our product and confident that with that yield increase that we've seen in our trials, your growers can benefit from this strategy, especially some of those more progressive, proactive ones that are looking at doing a little bit more to accurately and effectively manage their soil's pH. One of the last things here that we've got some slides on was a study done by the University of Illinois where they utilized 98G as a liming material and compounded that with some applications of phosphorus. That kind of going back to that age-old adage that you shouldn't apply your phosphorus and your lime at the same time, and they wanted to really investigate that a little bit further. And what you'll see with the results as we step through them here quickly was that they found out the exact opposite, that there was some synergistic effects by applying both products in that same application window. A little bit about the trial information. You can see pH is 6.4 already. So again, a soil that's not going to need any pH correction to grow a solid corn crop. This would actually be an ideal maintenance strategy or maintenance approach situation for us, utilizing that maintenance trial approach that we just talked about in the previous slides. So you can see they applied their 98G and their phosphorus applications in the fall, and then took soil samples to measure phosphorus availability that next spring. So you can see when we're not applying any phosphorus there on the x-axis, so you have 0, 40, and 80. When we're not applying any phosphorus at all, that 400-pound rate of 98G actually significantly increased phosphorus availability that next spring. And then when we applied more of a moderate rate of phosphorus at that 40 pounds of P2O5 per acre, just a 200-pound application significantly increased phosphorus availability for that growing crop. And you can see how that also was extrapolated here at the 80-pound rate as well. So that begs to call to attention that with phosphorus prices where they are this fall, maybe some growers are thinking about cutting those phosphorus application levels. And if they do that, one thing you could also mix in would be 98G to help maximize that soil pH and optimize that phosphorus availability for that growing crop, kind of quote unquote taking advantage of what they might already have available in their soil already before applying additional phosphorus. Okay, so next thing here, obviously corn grain yield we know is what pays the bills. So you can see when no phosphorus was applied, we had a significant yield increase at the 400 and 800 pound rates of 98G. When we applied just 40 pounds of P2O5, it only took 200 pounds of 98G, and really there wasn't much of a benefit by adding additional 98G in that instance, and that really kind of mimics what we've seen with our 98G maintenance trial rates over over the last several years. And then when you get to 80 pounds of P2O5 per acre, you're getting to a spot where phosphorus probably isn't going to be a limiting factor. So as we would probably expect, the 98G is probably not going to show much of a response when phosphorus is not going to be a limiting factor in that soil situation. So kind of boiling things down here on 98G, how can 98G offer an advantage over aglime? As kind of Glenn talked about, a lot of those aglime sources that we talked about can be wildly inconsistent. They can have variable CCE, variable in the amount of grind that takes place that can affect the ECCE. Especially with products like water treatment lime or beet lime, that moisture content and the ability to spread accurately can really be hampered in those situations. As we've come to find out in my travels, aglime can be subject to availability. Those quarries don't have limitless supplies all the time. And so sometimes if you're not first on the list of getting aglime out of a certain quarry, you might not get any aglime that year at all. We talked about the advantages of 98G and how it can be handled and blended just like your other dry fertilizer products. And so in most cases, that can actually save you a trip across the field if you can find a way for 98G to ride with that fall or spring dry fertilizer application, whether it be phosphorus or potassium. So how can we use 98G? Again, this is kind of reiterating some points we made on the last slide. That application flexibility, that Iowa State research showed that with the speed of reaction and how finely we grind the limestone product before pelletization, really you can apply 90G anytime you're applying a dry fertilizer product and expect it to quickly react and start go to work neutralizing those soil pH issues. Blendable with other dry fertilizer products. I feel like at this point we've kind of beaten that horse enough. We have variable rate or flat rate opportunities. We have equations for those of you that might not have equations built into your system already. Again, reach out to your local rep or drop us an email. We can make sure that we get you access to those equations so you can go to work VRT and 98G yet this fall. And again, with that maintenance strategy, where the ideal situation is going to be those more frequent, lower rate applications that we can kind of use to mimic a dry fertilizer application. And again, what we see with those is what the University of Illinois study showed, is that with those lower rate applications, we can still maximize phosphorus availability for that next growing crop. All right, so that brings us back here to the importance of soil pH. And what we're going to talk about next here, I'm going to kick it over to Glenn, and he's going to talk about a calculator that we've built here with around the nutrient availability piece of this. And so I will go ahead and kick it over to Glenn. We can cover this slide. He can cover this slide, and then we'll go ahead and showcase our calculator.
Thanks, Josh. So we've known for the industry for a really long time, decades in fact, that pH affects the availability or the uptake of varying crop nutrients. Key ones obviously being N, P, and K. One of the things that pH affects is how well a plant can utilize or take up a given nutrient at a particular pH. So when we look at the graph there, or table on the right, so at a 5.0 pH, if we put 10 units of nitrogen out there, we're going to get just over half of those available for uptake. If we put 10 units of phosphorus, again at a 5.0 pH, we're only going to get about 1 in 3. And 10 units of potassium, we're going to get half again. So overall, those are out about half of those nutrients are available at a 5.0 pH. Bring it up a little bit on the pH scale to a 5.5. Now we're up to 3/4 of our nitrogen we can take. We're still approaching, but not quite to half of our phosphorus, and again, about 3/4 of potassium. So our overall efficiency, we're about 67%. One more step up to a 6.0 pH. Now we're almost 90% on nitrogen, a little over half on phosphorus, and all of our potassium. So the impacts of pH on varying nutrients, or particularly on N, P, and K, have been used for a long time and well known. One of the things that I've struggled with myself is just trying to put those into an economically conversation that relates to both what I'm dealing with as well as what folks like an agronomist yourselves look like, and most importantly, what a grower or farmer thinks about. So we went another step here and put it into kind of a worksheet format, which Josh is going to bring up on the screen now. And this is something, again, that's available for everybody to have access to. You can download a copy if you like. We just have a little process through our website to do that. But what we've done is take these varying things, the very factors, apply them to commonly used fertilizers, and then thrown in some economic values that you'll find today.
Glenn, can you see that?
I cannot.
Okay, hold on here. Let me go ahead and... How about now?
Yes.
Perfect.
Good. Thanks. So the values there in the yellow cells are ones that can be modified. So what crop are you going to raise? What kind of yield goal do you have? What's your soil pH? So in this example, raising corn, trying to raise 225, and we have a 5.0 pH. Underneath there, we got some varying fertilizers, and those are all available for a lot of choices again, with the yellow cells being what's the price of that varying fertilizer. So in that example, we put on ammonia around 550 a ton. We can use MAP or DAP or other phosphorus sources, potash or other potassium sources, as well as sulfur ones. So in essence, is what we've done is taken the evolution a little bit further and put things into a perspective that I think you may find a little more valuable. So in terms of what does that matter? If we put on, in this scenario, our total investment is around $170 an acre to put on the crop removal equivalents for NPKs, based on this particular example. If we have a 5.0 pH, we've got a lot of dollars, about half of them, in fact, that are at risk. At risk in terms of they are going to remain in the soil in most cases, but they're not going to be available for plant growth. So the plants can't use them because of the impact of soil pH. Particularly a focus again on the phosphorus aspects. I think that's the one that's, to me, most important of those three in terms of its effect by low pH values. If we use and change that soil pH value up the top there and go up to a little different one, 5.5 is great. Yep.
Oh,
and
sorry.
show that value on.
There you go.
It looks at, so again, the overall cost per acre, $170 an acre, that hasn't changed, but our overall efficiency has. So we've taken that from about an $80 at risk down to about $50 at risk. Again, those materials are still going to be there in the soil, but the plants can use them much more efficiently at a 5.5 pH, but still not as effectively overall as we would like. So in essence, this is just putting some metrics to things that we've already understood, but in a way that we haven't really thought about specifically, at least I haven't seen previously. So again, this is something that you can download through our website. Andrew, I think, put a note up in the chat there. Just send an email to agronomy at Calcium Products, and we'll get things sent your way so you can look at this and do run some things example for yourself and for others if you choose.
Yeah, one thing to add quickly is most of the time it gets through okay to people. If for some reason you don't see that email come through with the calculator connected to it, let us know. And in another, if you don't get it in the next day, let us know. But do check your spam or junk filter or folders if you don't see it right away. But we'll get it to you one way or the other. If it does not show up in a day, let us know at agronomy at calciumproducts.com. We'll get that sent over to you.
All right, thanks, guys. So I think that will kind of put a bow on our first session of the webinar for this September 2025 edition. Again, like I mentioned, if you utilize that email, agronomy at calciumproducts.com, for those of you CCAs, or if you have any other questions, want to carry on the conversation, go ahead and drop us a note, drop us a question there. But first and foremost, on behalf of Glenn and Andrew and myself, I'd like to thank you for your attention this morning. I know this can kind of be a busy time for a lot of you as we're getting and making preparations for harvest. But again, from Calcium Products, we'd like to thank you for your time and your attention. and wish you a safe harvest season. Thank you.